Hey, welcome everyone to Omaha Data Science Academy. This is SQL 101 Fall 2005 session. I am Jeremy Bergman, the instructor, and this is class 6. This is advanced database functions and SQL performance. So tonight we're going to go over some advanced database functionality that a data analyst would likely use in their day-to-day jobs. Some of these include some data structures such as common table expressions and data or temporary tables that make taking complicated queries and help you break them down into pieces to make them easier and possibly even more performant and perform better than a big complex query. We'll also learn some advanced database functionality. We'll learn about procedural SQL tonight. So throughout this class, we've learned about the basics of SQL and queries and the things that you can do for that. Almost all these relational database functions have a type of procedural programming language in them. And it's good to know it as a database analyst because you can deal with things like build your own functions or build your own multi-step routines that instead of just doing one step, you can use multiple result sets in the same set and do a bunch of different operations on data. And then the last part, we'll learn about some advanced aggregations and use for analysis and some performance tricks on your SQL queries. But really combining 2 into 1 here, so we're covering a lot, but we'll have the video here after lecture for you to review. A lot to cover tonight. All right. So I gave a good overview, temporary tables, common table expressions, just a couple of different types of almost data structures to be able to hold result sets in memory or be able to reuse that result set multiple times. And we'll see where that comes in really handy, some specific types of analytical challenges you may face as a data analyst. You have standard versus procedural SQL. I gave an introduction to that. So standard SQL is what we've learned throughout the class. It's that language used to communicate with the relational database and either get back the data or manipulate the data that's already in the database, however you need to do that. Procedural SQL, you can combine SQL with some features of programming languages, especially the multiple steps. We'll see where that's useful. I use it quite a bit in data as a data analyst for reports or potentially data warehousing. I'll describe that a little bit, where you may see that or use that in your day-to-day jobs. And then procedural syntax. This is what we'll cover during the first hour. And then the second hour, we'll cover more about performance and Windows functions and stuff like that. So that's what we'll cover. So why do these advanced techniques matter? Oh, sometimes I go straight into these things without saying, why is it important for a data analyst? So, hey, you'll solve some of these common data analyst challenges. So without some of these features, it may be multiple steps. It may have subqueries within subqueries, and it becomes really complicated and difficult to wrap your brain around, or it's tedious. Or you have to go back a month later and remember what you wrote in code and the different rules and recreate some of it. So there's data structures to be able to help you with some of that challenge, help you with that, especially that subquery challenge. Or the query's been running for 10 minutes. How can we improve on the performance of this query? There's temp tables, there's some intermediate steps that you could take instead of doing some other things. We'll see how that would work. And then how can I calculate running totals? So we'll do this in the second hour with these aggregations, but there are different ways that you could summarize the data. So what the group by does, it collapses the entire group. So group by group that you have in your query, it will sum or average or get the median or the variance or whatever function, aggregate function you'll use. It'll collapse on the entire column. But this will be like, what if we just want to do a running calculation over each one of the groups instead of collapsing them? So there's some Windows functions that we'll be able to do for this purpose, and we'll see how we can use that. So even in Tableau, they have like running totals or Windows functions in Tableau. It's a similar concept. So with these skills, you have CTEs. We'll write a query once and reference that query multiple times. We'll see how that works. Just talked about Windows functions and how we can optimize queries. How do you solve that problem if it's running for 10 minutes or even like an hour? How do you break this into different parts? What types of considerations can you do for your query to make the result faster? Potentially an interview question. I've had it before where somebody asked me, like, how would you design a query for the best performance? So there are a couple different techniques that you can do with columns and rows, and then thinking about how you're joining and bringing these tables together for your final result set. So here's a real example of sales analysis that took 8 minutes. Can be run in 12 seconds with the proper query structure. So instead of taking 8 minutes, you can do some shortcuts there, run it in a fraction of the time. Okay. So first, we are going to talk about CTEs and temp tables. So let's give a business scenario. Let's say your manager asks, show me the customer lifetime value, but only for customers who've made purchases in the last 6 months, and compare their average order to their category average. So we're doing like a sum over that entire customer, and we're doing a sum over the category. And then we're doing customers only over the last 6 months. We'll see where we could structure this. So sometimes in analytics, these queries, they can get pretty complicated as far as like, it's not that hard a question in itself, but you have to kind of break it down piece by piece and think about what subset of the data do you want for each one of them? What's your aggregate level? And since there are multiple aggregate levels, it's actually pretty hard to bring together in one query. You could do it with subqueries and then joining them all together, as we'll see an example. It's probably not the best performance necessarily, but we'll see a data structure that can help us out with that with CTEs or temp tables. So to do this, it would require filtering recent. You think about those aggregate levels, filtering to recent customers, calculating their metrics, then calculating their category averages, or multiple categories under each customer, and then joining everything together. With CTEs, you can break this down into multiple steps. So oftentimes where you'd have a bunch of subqueries, CTEs or temp tables would come in valuable. And then just a slide, if you're not familiar with customer lifetime value, it's basically measuring customer profitability and then trying to determine how profitable are they now and then how profitable would they be into the future. Both of those combined would be a lifetime value. Type of analysis you may be asked to do as a data analyst. I've done it before myself. So kind of describing the business scenario, let's talk about now what are temporary tables and CTEs. So temporary tables and common table expressions both define temporary result sets that can be referenced in query syntax. So a temporary table is really just like a table, but you're just temporarily holding results in it to be able to use it in multiple places. So temporary tables exist during the duration of a database session. So whenever you're logged into the database, if you create a temporary table, it stays there until you log out of the database. And oftentimes, temporary tables, I do it a lot. I use temporary tables a lot. If you don't really need to store data in a permanent table, you're just doing something for analysis and holding a temporary data set or result set, a temp table is perfect for that. And you notice you have the same type, you define it in the same way you do as a table. You just use this keyword temporary, and you define your primary key, and then your data types or your field names, your data types. You can put constraints on it and everything if you'd like. Same as a table. I find it very useful to do inserts into. You could do inserts into a temporary table from another one and do like an aggregate for analysis and keep those results there. Plus, it helps me break a complicated query into multiple parts, and we'll see also where sometimes you get better performance out of it too. So temporary tables, they exist during the duration of a session, and tables are better for separating data and storing results that may be used multiple times in a session. So I was just saying, if you're using that temporary table in multiple places in an analysis, it's a good use for it. Temporary tables are also useful if you're storing a large data set temporarily. Maybe you've limited it down, you do a summary. Maybe it's a 30,000 row summary over a bunch of customers. Temporary table can be a good structure for that. So a common table expression, we keep using this term CTEs. It's called common table expression. So you can express a query like a table, and then you could use the results of that query inside of your subsequent query. So these CTEs, they only exist for the duration of the query. So they only exist once you hit run on the query. But the usefulness of this is that it can simplify subqueries or joins and allow more complex operations like recursive queries. So queries that refer to themselves. So one of these could be some type of hierarchy. So maybe you're doing a summary on a city level, or a country level, then a state level, then a city level. You could do each one of these summaries with a CTE and then use it in your final result set instead of trying to combine all those aggregate summaries into one query where you'd have to use subqueries to do that. But we'll see an example of this coming up. Specifically, when the CTEs simplify those subqueries, especially if you have nested subqueries and then joins. And I think overall it helps simplify the query. We'll see an example of that. Okay. So we're going to build the CTE. I did not put this in here, this query in here super well, but we're going to start with a business question here. I'm going to copy and paste. Try to copy and paste all of this into, I'm going to do this into Slack first. Let's see, which slide was this? Slide 6. We'll frame it with this challenge first. Okay. So what are we trying to do here? We're trying to do a couple of things. So we're trying to start with the business question. You want to get who are the top 5 customers by rental account. So this is just a simple CTE example, but I give you an idea of what you can do. You can break it down into logical steps. So you can create part of your CTE that does a count of rental customers and then ranks the customers and then gets the top 5. And then you could use that in a CTE, use that inside of a regular query, and then get the customer information. So instead of thinking about how do I bring all this together, you can do it step by step with a CTE. And then once you do that, you can use them all in this final query. So let's show you what this looks like. This is not well formatted. It's copied and pasted into here. But I'll repaste this once we start doing this inside of my SQL workbench. All right. So a CTE, without going too much into the syntax, it always starts with, and this will be the name of your CTE as top customers. You can use this like a table or result set, an alias for a result set. And then you see the as statement. So we're going to do steps A and B from that slide. We're going to do the customer counts, and then we're going to get the top 5 customers. And this looks a lot better once I start to parse this out. Look, notice like a subquery, you have the open brackets and the closed brackets. That is what contains your result set within the CTE, common table expression. So that's why it's like a subquery, because you put the subquery in between the open and closed parentheses. And then you could use this CTE within your main query. So we just want to focus first on those customer IDs and getting the top 5. And then we could use that CTE by name. So we use it as a table in our final query as top customers. And then last, we focused on getting the customer information for these customers. And just a note, we are currently using the Sequila database for these examples. So you could put schema.table, or you can go up here to use. Set it as default schema. Either one will be okay. So I really like this because even with subqueries, you can run this in parts and really just break down the challenge. That's what I always do when I have a challenge of just conceptually struggling with like how I'm going to bring all this data together for the request, bring the data together for the request. So you can run it in parts. You can get all the customers. And then remember at the beginning, if you're ordering by the rental count descending and limiting the number of records to 5, that is going to take all these from top to bottom. And then you'll cut it off at 5 and get your top 5 customers. And there's the rental count. So now if we run this, we can take that result set that's in the CTE and run it in our main query, where we join the top customers by customer ID with customer information in the Sequila database. And then you can get the names for each one. So really good way of breaking it down. You could even have, maybe I have an example of this in the next slide, but you can nest CTEs within CTEs. So you can have as many CTEs as you want. The result set of this will just carry into the next CTE until you get all the way to the final query. And if anyone has questions along the way, please feel free to drop a message into Slack or StreamYard, because I'm going to go through it relatively fast. And I'll put this formatted query in here so it looks a little bit better into Slack. Also try to get everyone an updated SQL file for all the lectures here. So feel free to keep all of the PowerPoints and all the content for this class, and I'll update that SQL file, and you'll have that, and you can always run back through all of the slides to remember certain things that we learned in class. Okay. If there aren't questions, I'm going to keep moving forward. I think the next slide, I don't have an example here, but if we get to our exercises, I know that I have a multi-step CTE example in our exercises to end class. Okay. So key insight is that CTEs let you think in steps, not nested complexity. Nested complexity can really be hard to unravel. And it's just like easier readability and everything for the query. It's easier to know what another analyst was doing or yourself sometimes. If you look at code for the first time or months later. Okay. From the current slide. Okay. So, screen's all over the place. From the current slide. Seems slideshow. Oop, I do have the slideshow over here. Okay. Subqueries versus CTEs versus temp tables. We didn't do much of an example for a temp table, but if you were to use a temp table, actually, I kind of like to do a quick example of that. It's really pretty straightforward. You could use this query instead of a temp table. This CTE. So you would do a table, temporary top customers, or create temporary table top customers. And then you could do an insert into. And my syntax isn't quite right there. Give me 1 second. So just showing how you could change a CTE into temporary table, I think is useful. Top customers. Said insert into table. No. Create table top customers as. Let's just try that. That's not right, so I'm gonna ask real quick for the syntax.
I think it should be create temporary table instead of table.
Create temporary table, there we go. I hardly ever commit anything to memory, but I wanted to show everyone what this would look like as a temp table. Oop, there we go. It inserted the 5 records there as close. Thank you for that. Help. And then I've created this temporary table that I can query just like a table. select star from top. Something unplanned a little bit, but I did want to show everyone what this would look like as a temporary table instead of a CTE. You just insert it into a table that you can now query like it's any other table or result set. And then it's essentially like really similar. So we have this top customers table now, temporary table that we can query. In some relational databases, they'll have you use like a hashtag or something to indicate that it's a temp table. You don't have to do that in MySQL. So we're going to get first name, last name from the customer table. We're going to get the rental count from this temporary table that we created called top customers. And you get the exact same result. So I wanted to do that to just show you how you can also break that down into a temporary table in a very similar way. I like to do this if I have multiple aggregations and I just want to break it down into multiple steps and then join them all together. That's oftentimes where I use that. Whereas CTEs, I would use that more often for my nested queries that we saw before. So I'm also going to give everyone this example too. Use the temp table. Okay, drop that in the Slack. All super valuable for data analysts, especially when the queries get complicated. They're my two favorite tools for doing that. And then once in a while, I'll also use a view. The challenge with views is that they have to materialize as a result set. So the database has to, if you're using that as a table, it has to run first and then get all the results and then use it in the query. Whereas a temp table already has the results in it. So temp table will always be faster, but sometimes I'll also use, if I have a view with an aggregation that I like, I may use it in a query, or I may just take that view and then insert all of the records into a temp table like this, and then just use the temp table or get whatever records I want from a view. Those are a couple of my favorite tools as a data analyst to use. I wanted to cover that because I really wanted to cover how you could use this on the job. All right. So when to use each, I saw this slide and I decided I wanted to back up for just a moment and show everyone how you could also use temp tables. So quick decision matrix. If you're doing simple filtering, a subquery may be useful. Or if you're just doing one subquery within a table and it's pretty straightforward, there's nothing wrong with using subqueries within tables either. I would say if you're using it in a where statement, if you're using a subquery to filter out values for a where, in general, I would try to have as few of values as possible, but it's not always possible either. So if you have complex multi-step logic, that's CTE would be good, like the lifetime value. If you were doing things like calculating customer lifetime or revenue, and then the next step you have to calculate profitability, and then you have to summarize it by some type of product group or customer group, and then bring in a bunch of results at the end, that would be perfect for your CTE. Customer lifetime value is a really good example of that from what I've done in the past, where it has multiple steps, has different aggregate levels that you were considering and using in your queries, and then you can bring it all together step by step, even in multiple CTEs that you utilize each other. If you have a large intermediate result, temp tables are good. So instead of running a big subquery review, like I said, that has to bring all the results first, you can put all those results in a temp table and your query will run much faster. Plus, I just like temp tables as like a check for myself. Like, are these exactly the customers, or is this the exact summary that I want to use inside of another query? So you can do recursive operations in CTE. You can use multiple steps that build upon each other. And then you can share data share across your same session in a temp table. So as long as your session's open, you could use this a temp table to, for example, maybe you have some type of inventory summary and you need that inventory summary in multiple reports. You could create your temp table first and then use it in multiple queries, in multiple reports. It could be useful for that. So very much tools that a data analyst would use. Complex ETL operations and multi-step data processing is used for them too. I use it a lot in the ETL operations. And next we're going to see stored procedures. And I love temporary tables and stored procedures. And we'll see how that works. Okay. So now we're going to shift the discussion to standard versus procedural SQL. We did a primer at the beginning of what this is, but diving a little bit deeper, your standard SQL refers to the syntax and semantics of the SQL programming language. It's a common language used to communicate with databases. It's what we've done throughout class. You have the different clauses like the select, from, where, group by, order by, and so forth. Each one of those is executed, statements is executed one at a time. So that query is executed in isolation with itself. It means it's non-procedural. The language generates the logic to the database. The relational database generates the logic from the SQL that you write it to get exactly what you need from what you wrote, what you instructed it to do. So it's really one state you write, one statement, you get it back. Procedural SQL is an extension that enables developers to include constructs like procedures, functions, and triggers. So almost always the advantage of procedural SQL is that you can put multiple steps in it instead of one. So you could have one result set, you could store it in a table, then you could use that table in another query. So think of something, data warehousing is the example that I wanted to do. Oftentimes in data warehousing, you have extraction and then some cleaning of the data, summarizing of it, you do all of your checks. It's a multiple step process that fits perfectly into a stored procedure. So if it's multiple steps, something like data warehouse, you're taking data and cleaning it up and storing it for a data warehouse. That'd be perfect use for it, or a multi-step report. As a data analyst, you can create your temp tables, then use your query, and then produce results, and even have parameters that you use. You can have parameters in here. So you could do a get all products and put a product ID in here. So it gets you that product or a set of products. It's really good for creating reports also that are multiple step. And the code is processed in the order that each statement is written from top to bottom. So there's a more extensive resource here if you really want to dig into it. My intent is, especially for data analysis, is to introduce these as tools for you to use that you can learn and build upon later if need be. Yeah, so going from procedural SQL, we'll learn about routines. There are two types of routines before we get in more into stored procedures. So for data analysts, these two include stored procedures and functions. So you can actually create your own functions for analytical purposes. Usefulness of this is like a business rule that you want to just create a function for. Maybe it's an aggregate, or maybe it's or potentially it's just a scalar function. But either way, it has some business rules, and you have the ability to create your own SQL functions. You'll commonly use these for special calculations like fiscal quarter, or getting like if you have a bunch of logic in here or if you have some logic in here to calculate the customer lifetime value, you could put that in there in this SQL routine and run through it and then return the customer lifetime value for that customer. You can do something similar with stored procedures, often useful for repeated reports, like your monthly sales summary or your customer cohort analysis. So what I found in my experience is that it's really easy to write queries in SQL code, but part of the challenge is that you could write many, many versions of it, and then you forget which version is the current version, or you forget how you updated it potentially over time. You can store all of this in a stored procedure. So you can store all that business logic so you don't, forget how you wrote it or how you did it. It's just stored in your procedure. The multiple step process is stored in your procedure. Very similar to views. I think views are a place to store a single query with business logic in it. Stored procedures are a place to store a process or multiple steps with business logic in it. So you could do a monthly sales summary or like a customer cohort analysis. Maybe you're taking customers by quarter. Maybe you're using a fiscal quarter and then doing some calculations and bringing some data together to create that report. So it's a good place to encapsulate business logic with multiple steps. There are also triggers, database triggers in MySQL, but I've hardly used them as an analyst. What these are is things like if you insert a record into a table, is that it looks for an insert or looks for a field that's updated, and then it updates another field, or it does some type of action. It triggers some type of action. So it's a create, read, update, or delete operation. So if something happens, an insert or an update on the database happens, it triggers something else to happen in the database table also. So don't worry about it too much unless you'd like to know more. It's mostly for like complex transaction logic. It's mostly out of transactional systems, not as much for analytical purposes. So let's do a real use case, real life use case for SQL routine. So your team calculates active customer differently across 5 different reports. Create a function, is active customer, so everyone uses the same definition. So this one isn't that example exactly, but you could create a function and it has an as of date, a customer and an as of date, So when they were active as of. So you probably have some type of logic. There's probably some criteria to decide if a customer is active or not. You could put that criteria inside of that function. And then is the customer active of that as of that date? Do they meet this criteria or not? And then the function would likely return like a true or false or yes or no or whatever it might be. So an example of this routine, here's a stored procedure. It always has a couple of different parts. So you're always going to create either a function or procedure. You're going to give it a name. You'll give it some parameters, so the types of data that you would feed into it. So here's an update salary function with employee name and increase amount. And then it always has an alias as, and then a begin and end statement, so you know where the logic begins and ends. And then you have operations. So you're going to update the employees table. You're going to set the salary of the employee to salary plus increase amount. So the amount that you increase, you send to your function. Like here, we're going to run this stored procedure and update John Smith's salary by 1,000. Where the name is equal to employee name. So not just this, you need to know that you're going to increase the salary, but what employee are you going to increase that salary on? So that's where you get John Smith. You'd feed in the employee name, and you feed in the increase amount, and it'd update the salary, John Smith's salary, and increase it by 1,000 in the database table. So I haven't created a ton of functions, but there's some specialized cases where we've created statistical functions and special calculations and stuff. Usually you could create this type of logic into a query itself, but on occasion, a function will come in useful or handy or useful. So especially if it's like a business rule that you just want to apply over a whole bunch of different reports. Maybe you have 100 reports and you just want that business rule in the same place, so you don't have to rewrite that business rule like 100 different times. Or if the business rule changes, you don't have to rewrite that business rule in 100 different places. You just have it in this function and you do it once. So it can be useful to create your own functions. It's a lot like creating a calculation in Tableau, but usually these functions are like multiple steps. All right. So we're diving into stored procedures. Stored procedures, that collection of SQL statements that are saved for repeated use. As you notice, you have the create procedure. You have a create statement and begin and end with all of the logic inside of it. So you can have a SQL statement like this. You can even have some if-else logic and some error handling. This one doesn't. It's just a basic example. But you see where you have a query, and probably one of the more useful things are these parameters. You can say we take in a customer ID, and then we can filter this query by that customer ID, and then return the result. So really good for parameterized queries and reports. That's one of the uses I see the most. So stored procedures, we talked about this, but it's valuable for enforcing business rules, implementing complex transactions or logic, and saving that for future use. Procedures will return a result set or value in return. So you'll either return the whole results of a query or a single value. It can be either one. So in this case, you would return a result set. You would return title, rental date, return date of this customer with customer ID equal to 5. So the example is getting the films rented by customer. We'll see this in a second, using the customer ID field as a parameter. Okay. So let's go ahead and do this. I don't really have it in a copyable format, so I'll just go ahead and write the query. Let's just go ahead and do a new one so I could hand these out to everyone after class. So, stored procedure example. So create, so some keywords, always in blue in MySQL. We'll give the procedure a procedure name. In this one, we actually want to get customer rentals. We're going to take in a customer ID. And then we define that data type that we can have as input. In this one, we don't need any parentheses. We just need the begin statement, the end statement, and this statement called delimiter. It just shows that it's the end of, that's the delimiter that we're using to denote the end of the stored procedure. Okay. So we're going to select f.title, r.rental date, r.return date from film F. Nope, not autocomplete. From Sequila.film. We're going to join Sequila.inventory on film ID. Join rental. Or on I dot inventory ID, where limiting the rental table to where the customer ID is equal to that customer ID that we're passing into the stored procedure. Order by r.rental date descending. And that is where we use our colon that we identified in the delimiter to show the end of the query. Use our end statement to denote the end of the stored procedure, and that is our delimiter. And let's go ahead and not create this in the Sequila database either. Let's go ahead. Create that in our own schema. So that'll show up as a stored procedure there, which is just fine. We're just reading from this database, and we can create the stored procedure that we can rerun and execute in our schema. And it says that there's a syntax error. Where did I go wrong here? delimiter because we need a delimiter at the beginning to start and end. Let's see if that executes. No. Let's see, what else could we be missing? You may need these forward slashes too. Also needed the forward slashes on this, the delimiter and the end. Okay. So now we have our stored procedure. You can see that as a database object, whether it's like a table or a view. Did refresh all. We have this get customer rentals stored procedure in our database. Now it contains all of this logic that we could run on any customer ID. You could even send this to a SQL editor and do a procedure call to see how you would call it, but how you can just write this as code also. You can simply just call J Bergman get customer rentals. It shows it. And then you enter what your customer ID is. So maybe we'll just want customer ID 5. And you run it. And I am surprised that we get a whole bunch of results there. Let's see something, why that would be. Let's put r.customer ID in here. And after you create a procedure, you can always, after exists, you could alter a procedure. Or should be able to alter a procedure. Or just for the moment, we'll just do create procedure 2. Okay. So I want to see, we're like, why did I return so many results there? Are there that many customers with customer ID equal to 5? Not sure. Okay, so we're just going to create another one. If we refresh this, you can alter a procedure also. I'm just blanking on. There must be some small syntax change that you need to do here that I'm not thinking of at the moment. But now we have our get customer rentals 2.
Can we get the code? Can we get the code for that?
For this?
Yeah. Just
I'll paste
the select part.
Here, let me just go ahead and paste it now. I was going to paste it before. There you go. So you can play around with it while I'm talking. But yeah, I'm going to paste all these in here since I don't have them in that SQL file. Oops. We don't want to create that. We just want to call it. Yeah, and there actually are a bunch of customers in this database with customer ID is equal to 5. Oh, you know what? Yeah, so this is it returns all the films for customer ID is equal to 5. This is all the films they've rented. That's why. So customer ID 5 and all the films that they've rented, it returns that entire result set. So this stored procedure is returning a result set. Instead, if you did here and you just did a sum, then it might just return a single value. for that customer. If you just counted the number of movies that the customer ID 5 is rented, you can just also return a single value too. So especially if you have multiple steps, you can use temp tables in here. You can use CTEs. You can take the result of one data set like that, store it in a temporary table and use it multiple times. I frequently do that within stored procedures and encapsulating business logic into it. So one of the more extensive ones I did was to capture inventory changes from a system on a daily basis. So I get all that data, I'd store it in a temp table, do all the calculations that I needed step by step in a stored procedure, and then I would store those in an analytical table that we used in dashboards. So especially good for ETL and data warehousing or multi-step reporting. And then you can use things like inserts or updates. You can insert new records or update old records based on changes in a database also. All right. I am going to we'll try to get to the end of this section and then give everybody a break and let everyone ask questions. Okay. I want to give everyone plenty of examples that they can review, go back and review also. Okay. Stored procedures. Let's see from current slide. Every time I move it over 1 second. There we go. Okay. There's an example of get customer rentals. Really good for capturing the logic. Here's a practical example. So a real analyst use case. This may use both a calculation. You can create a function and put it in a stored procedure. The analyst use case is creating a monthly sales dashboard. You want to run the same analysis every month. You want to get sales by region, top 10 products, year-over-year comparison, and customer acquisition metrics. So you could even do multiple reports out of the same stored procedure. Maybe you're doing a stored procedure that stores the sales by region and top 10 products in year-over-year comparison. Maybe it's all storing it in tables so that you can load it all into a Tableau dashboard with multiple tabs in it. That can also be useful. So the benefits of that is that there's one source of truth. You know exactly your calculations and where they're coming from. That can be a big deal in a big organization. Once you start to get asked like how everything was calculated, it's already right there in a stored procedure. You don't have copy or paste errors, so you aren't running multiple queries and copying and pasting them into Excel sheets or running each step yourself, and possibly maybe you accidentally ran an insert, you duplicated an insert or whatever it could be. Stored procedures are super easy to schedule and automate. Most relational databases will have a scheduler that you can just run these weekly or daily or monthly. And then you could add those parameters that are useful for reporting too. So it makes it more dynamic instead of having to run a single, maybe having to run a single SQL query multiple times on multiple date ranges and filters to get all of your results. Without it, you might be copy and pasting those 200-line queries every month. That's prone to errors, and everyone on the team can have slightly different versions. I've run into this, especially at the beginning of my career, a lot, even in organizations that don't have all these things defined. There's like two versions of what seems to be a sales report, but things are defined slightly differently. You can encapsulate that all in a stored procedure where all the analysts could use the same logic. So with the stored procedure, you could create this sales report. You enter report month as a date, and then you put all of your logic and everything. You get your consistent results. You call it using that procedure name in that date as a parameter. And then you have all of your monthly sales analysis and reporting for October 2025. And then you could easily do that each month. You just run this piece with all of your logic in it every month to generate the same thing. So stored procedures have been a big part of defining this, like slightly different versions or the source of truth, and then automating those tasks, and then just being able to keep track of all of it instead of having 50 different SQL queries to run. Okay. So functions, we've covered this pretty well, but a routine that returns a single value given the function's parameters. An example would be calculate the rental ID as a parameter. Rental ID as a parameter in days. So you're calculating the rental duration, the current rental duration in number of days, or you're actually calculating the number of days a movie was rented or currently rented. So you could use it in a query like this. You could do select rental ID. You create this functional rental duration or rental ID. You can get the rental duration. You have this function you created, rental ID, on the SQL rental database. So this is a scalar function. It'll go rental ID by rental ID, and it'll do this logic that you put in a function. So let's look really quick on how functions work. So you can create a function name, or if you create function and then a function name with parameters, very similar to a stored procedure. And then you say, what does it return? What kind of return data type does it return? So it'd be like an integer or so forth. I actually forgot what deterministic and non-deterministic is, but you can do things like, say if a function, how it modifies SQL data. So it can read it, it can modify SQL data. Then I forgot what the other two are. I don't use those other two a whole lot. But you declare, in this one, you declare your variables in a function. So you say if you have a variable that you're going to use in your function, you declare it as a data type. Kind of like a function you'd write in a programming language. You'd have your statements, SQL statements, and then you'd return an expression. So very similar to like a programming language. We'll learn a bit about it in Python, but how you could write a Python function on data to manipulate data. So what does this look like in real life? So you have your create function, you have the delimiters also, but you have your create function with the function name and then the column and the data type, your return type, and I'll have to look up what that is. I can't remember exactly what the deterministic is. And then you have your beginning and end statements. You declare any type of variable that you're going to use in your function that's not one of your parameters. And then you have this function. So for every rental ID that's coming in, you're going to calculate the date difference between the return date and rental date. So that's how long a movie was rented for. And then you store that single value into duration from the rental table, where rental ID is equal to this rental ID that you pass to it. And then you'll return duration unless it's null. Otherwise, you return 0. That's the if null function. Okay. So real quick, let's do this one also. All right. Do this as an example. I'll actually copy the stored procedure that we created in the last one because it has a lot of similarities as far as the structure. And note that each one of these relational databases, the MySQL or SQL Server or Oracle, this procedural SQL is going to be a little bit different in the syntax and then how you create stored procedures and parameters. It'll be a little bit different for each, but the intention is to give you some of the basics of how it's done and what it's capable of. And that the vast majority of relational databases have some type of functionality like this to be able to write logic or multiple step SQL, facility to be able to do more with it past just a single query. Okay, so stored procedure example. Not stored procedure example. We want to create a function. Get rental duration. Let's see, rental ID. And that'd be integer. We want it to return a value. We're going to define the return type. We're going to begin. That's where we start our logic, the end, and the delimiter. So we're going to, inside of here, we're going to declare duration as an integer. We do put a semicolon there, and we are going to do this date difference from the rental table. So I'm just going to modify this query that we had from the stored procedure r.rental ID is equal to rental ID that we're passing to it. So we want to select, we just want to calculate the date difference. We can use the date diff function as we learned just in our last class. And we want to do the greatest date first, the least date second to get a positive number. And we want to store that into this duration variable that we created. And then we want to return that value. But to be safe, we'll do if null r.duration or duration. Don't need to do r.duration because this is a variable inside of the function. Okay. All right, so, and we need a comma or a semicolon to enter query also. So this is looking like a decent query. We'll go ahead and run it, see if it works. If it works successfully, if the syntax is right at the very least, if we refresh, we'll now see our get rental date duration with this rental date. Rental date parameter is an integer, so you'll be able to know what type of data you need to feed into it. And then we can now use this in a query. So we can do select rental ID. This will help us with auto completion if we just use okay, so we want rental ID from Sequila.rental given an alias R, or you can always do as R if you'd like. Rental ID, and we want to feed it our rental ID. We want to feed that as a parameter, so we can use J Bergman get rental duration. We could even copy this if we'd like. And we want to do this on the entire column, rental ID column. So what this will do, this will work exactly like a scalar function would in MySQL. And this is where I could copy and paste it for everybody. Function example. It'll work exactly like a scalar function. It'll just go down this table one by one. Each rental ID that's in the rental table. And it will calculate the function. And it will return the result for each row in the column. So imagine the first row is 1. It would do this for rental ID 1, and then calculate the diff ID for rental ID is 1. Then it'd do it for 2, then 3, and then so forth. So let's see how this works. So that's what it did. So all these in the table, you have 4, 5, 6, 9, 13, 14, and it counts. It used that function to count the number of days it was the movie is rented. Down the entire row. So you can also create aggregate functions in a different way. You would do it using a group by and then returning a single result on a column. Okay. So we do have some examples. It uses both of these. It would use a create function. And then, let's see, we create the function. And then we do a date difference. So it'd be very similar. This is just a practical example of a function also. And it would do it as if it was an active customer based on criteria of date since purchase, less than 90. But I think for the sake of making it through everything and to our final destination here, we'll go ahead and skip the practical example since we did it on this one. Okay. So we're going to take a short break after this. I think it's pretty well deserved, packed quite a bit into the first hour, but we have temporary tables and common table expressions, how valuable they are for data analysts and where you can use them, what the best uses are for each one. We did standard versus procedural SQL. So standard SQL are just those single queries that we've been learning through the entire class, whereas procedural SQL allows you to combine SQL with some features of other programming languages, like we just saw with functions. You could create your own functions and return values and utilize that even within standard SQL. The procedural SQL gives you that functionality. Plus, you can create stored procedures that have that multiple step logic, or maybe it's even creating multiple data sets by storing data. You can do that, especially useful for reports and encapsulating business logic. Procedural SQL techniques. We saw the structure and the syntax, and then you have variable declaration. And then we had stored procedures and functions. We didn't learn about triggers because not frequently used by data analysts, but it is also a type of SQL routine that you can define and use. That was what we talked about, where if you have an insert or an update action on the table, is that you could update or update or delete values on another column, perhaps. It does another action on the table based on some type of insert or update or even deleted record action on the table. It detects those actions, and then it triggers another action on the table because of it. But usually used in transactional systems for table update purposes. Okay. Let's give everyone a nice break here. Let's give everyone 45, 47. We'll take a 15-minute break. Please let me know if you have any questions on the content so far. Say we're covering it. This one's some pretty heavy content that we're covering pretty fast. So feel free to ask questions. And we'll be back in 15 minutes, 7:45. And I'll grab a drink and I'll be here the majority of the time. So I'll be here in like 5 minutes. Get up and walk around a little bit. All right, see you in 15, and I'll be back. I'll be back here about 5. See you then. And feel free to drop any comments in the Slack that you would like also. Okay, I'll be right back. All right, everyone, I'm back for any questions you'd have. Still have about 9 minutes till we'll continue before we continue. Kind of doubling up on this lecture, but moving through it okay. So once again, if you don't get it right away, don't feel too bad about it. That's what the homeworks are designed for. Is that you see some you get the concepts and you see some examples here in lecture, and then you go try it on the homework. That's always, even in my technical classes, there's to repeat so many times. I got what they were doing, and like they had examples and everything, but I still had to just go like do the homework and go through it myself, and then like, oh yeah, I really get it. So once again, if you don't get it right away, use notes. Feel free to use AI to help clarify or to help. Try to have the homeworks out tomorrow so you can practice. The last two classes here, really applied SQL and what we learned in the first couple lectures of class, particularly for data analysts. Applied skills. And always feel free to ask if you're stuck. I remember there are a couple of things that I was going to ask. I forgot what they were in. I often work in Microsoft SQL Server, so I'm used to some of the syntax things there. But I forgot what deterministic and non-deterministic is. I'll put that in some notes. I'm going to look it up with ChatGPT right now. I do use MySQL, but I always look things up. I never commit anything to memory. It's probably my own challenge. So here's what I'm going to do. I'm going to bring out, bust out ChatGPT. I'll just bring this over here. I'll show you my history. Here's what I'm going to do a new chat. I'm going to say explain MySQL function syntax in this image. So you can just paste an image from the slide and ask it. Okay, so deterministic and non-deterministic kind of makes sense in the sense that deterministic always returns the same result, whereas non-deterministic might not. But I'm trying to think of a case where that would be. I guess if you were using the rand function or the now function, your now function is going to just get whatever the current value is right now, and that's always changing. And rand in theory is always changing. Or if it's reading changing table data, why does it matter? Needs this declaration for replication and binary logging. It's mostly logging and making sure they behave predictably. So if you put these here, for every operation, the database logs it. And then it tells you if the value is changing, that something might not be right with it if you choose deterministic. So it's more of like something that helps you diagnose issues behind the scenes. Okay. So the other part of this contains SQL, NoSQL, reads SQL, or modifies it. It says how the function interacts with SQL data. So I could explain the reads or modifies SQL data. So a function can change data in tables. You can write code to do that. You could tell it not to change data. NoSQL. This function does not execute any SQL statements at all. It's not like a NoSQL database. Maybe you're just returning a random number for some reason, or just pure computation. Or if it contains SQL, a function executes SQL statements, but does not read or modify data. Using control flow or variable only. SQL does. Why is this important? Does not enforce these rules strictly. Binary logging and replication safety, and affects permissions. So once again, it's just for logging in issues, and it makes sure that your function's not writing or changing data to a table when it shouldn't be. So they're more, and I think both of these might be optional. Or are these declarations optional? Not always optional. If you omit them, MySQL will assume default behaviors. In practice, often required. So we'll go with the base setting, and if it violates the base setting, it might throw an error to it. So the SQL Server doesn't even it doesn't ask you for those type of functions. So all these relational databases are just a little bit different. And I'm going to produce an example. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . MySQL procedural language. That's an example of an aggregate function here. Oh, it says that you can't create a true aggregate function as a function, or that you can't create a true aggregate function using the procedural language in SQL. Is what you can do though is do it with a stored procedure and then write an aggregate query. So here's a you could do it with a cursor. Or you can custom average function using a cursor. Usage example. I think that you could do it with a storage procedure. So you could give it a hard one. No, you have to use cursors still. But it'll give you an example of how to do it. That's what's good about generative AI. And then you output the CD input department ID, and then you'll output the average salary here with the stored procedure, declare variables, and then you use some logic to calculate it. So whenever in doubt, ask questions, allow generative AI to help you, especially with these stored procedures and functions and the syntax and everything, and save you a lot of time. Okay, let's go ahead and finish up this lecture. The rest of the lecture, make sure I'm back on camera. Right, the rest of the lecture. So we're really fitting 2 lectures into one here. It's looking pretty good that we'll get all the way through this today and do some more examples. But we are definitely squeezing a lot of information into this. Okay. There we go. Okay. So hour 2, here's complex query development and performance. So in a lot of ways, it's advanced join techniques, but it's also using how you can use the where clause to your advantage and thinking about how the relational database management system works to help you develop these queries. There's some advanced SQL techniques. We'll look at Windows functions and ways to calculate these that are faster than your typical queries that you would have to do in multiple parts with multiple joins. Maybe you would do it with CTEs, but there are some useful Windows functions that you can use for different types of summaries and aggregations than just using your group by statement. And then we're going to talk about how that's different. Join optimization. So that's one of the biggest things, how to optimize your joins, the difference between inner and outer joins and performance implications, and then multiple joins. At the end, we'll evaluate a query that's not necessarily poorly written, but could be much more efficient from a performance standpoint. That uses some joins and subqueries and multiple table joins and so forth. and learning some best practices and things that you can do to help with the query performance. Okay, so teaching this section for the first time to this class, so hopefully everybody finds it useful, but really now applied SQL. And as a data analyst, oftentimes you'll run a query and you'll know it's not that efficient. You put it together for the first time. Doesn't run that well, but you get the results. But eventually you want to say, how can we run this, like, instead of it taking 10 minutes, like the other example, or 8 minutes, maybe you can just run it in seconds. Makes your job much more efficient, potentially. And just good practice if you're running lots of queries on a database for those queries to be efficient as possible. So advanced aggregation techniques, teaching this section for the first time. So what is the problem? We're going to learn about Windows functions. So Windows functions, you can define these to calculate all of these different aggregate functions or rankings or values over a defined grouping. So if a manager asks, show me the sales with the customers, show me each sale with the customer's average sale amount. So the key here is that as a data analyst, you're always thinking about your aggregate levels. So you're thinking about, is it the customer level? Is it the customer product level? Is it product level summary? What is your aggregate level? What are you trying to summarize to? If you ever asked a question like this that says, show me each sale with customer's average sale amount, you can tell that it's on two different levels. So that's each sale would be the individual sale, and this customer average amount would be on the customer level. So you're going to have two aggregate levels and potentially two queries that you need to, two different types of queries, or two separate queries that you're going to need to bring together. We also learned about CTEs, which is a potential good solution to this too, because you just get the customer average. You could get the customer average and then use this in a main query. But we're going to show also how we can do this with a window function, which is sometimes a good answer or result. So your first instinct out of us, instead of a CTE, it might be to do a self join, is get each sale and then do that average amount on your customer. So you're getting each sale from the sales one table, and then you're calculating the average by customer from your sales two table. And really, I would think of this as a subquery. So maybe this is like a subquery where you're getting customer information, you're joining your subquery on this original table, and then you're calculating the average there. The problem with that is that your subquery has to get all of the customers and then rejoin it to this sales table, which is complex and slow. And we'll go over the example of this in a second. So with Windows functions, what you could do is you can do that first aggregate level, but now we can use a Windows function to calculate the average amount over your defined grouping. So you can do the average amount over, and then you use a statement partition by. So you're partitioning the table by a certain segment, like customer ID, and getting your customer average that way. So it actually, instead of writing like what they call a correlated subquery here to calculate it, which takes a bunch of time, you can use this Windows function and make it simpler. And it says in a way, Windows functions let you peek at related rows without collapsing your result set. So it allows you to summarize by these customer IDs without having to aggregate it, do that group by, aggregate it all the way down, and then rejoin it to your initial data set. So let's go ahead and see this. Let's go ahead and see this in action and like the difference. Let's see the difference in performance here. Okay. So I'm just going to go ahead and create a new query. So if we did this first one, let's copy this out. I don't really like how it was in this slide. We'll put # for comments. Okay. So actually how I would do this is I do a join, which implies inner join. If you do just put join in there, it implies an inner join. And we would do a query, subquery here. We'll leave this on statement for the end. Okay, so we're going to get this from the sales table, join, select. Pretty easy query to break it down into parts. We will just do the customer ID. Yes, S2.amount is sales amount by customer ID. Okay, so we do customer ID. Let's do a customer ID. And then we do average function, and then amount. I always like to use aliases just to keep things straight. As customer average. Always, when we're using aggregate functions, do the group by. Yeah. So this should get your average amount, sales amount by customer. It says table sequela.sales does not exist. Is this a sales table from somewhere else? I think it is. Okay. Well, this example may not work because I thought this was from the Sequela schema, but Sequela doesn't have a sales table. Let's see if we can come up with something real quick. Rental. How about rental? Rental's just the rental dates. Payments. Okay, we can do this and use Sequela.payment. And then we could use customer ID and amount from that. So customer ID and amount from Sequela.payment S, group by customer ID. Let's see if that works. That one did work. So here's the average rental for each customer ID. Let's go ahead and call this subquery as S2. Let's give that an alias. And then we can join that query on customer ID. So as that customer ID, and we want to actually change this to payment. And we want this to be, I believe, payment ID. Yeah, payment ID. So for each payment, what was the amount versus the average customer amount? Show me each sale with the customer's average sale amount. Okay. So we're doing this customer by customer. So we're getting all the payment IDs out of Sequila. Payment ID, what I think always helps. I always like to put the key values in queries. Let's do customer ID. So we're going to get the customer ID, the payment ID, the amount they paid on that payment, and then the customer's overall average payment as the customer average. So 2 aggregate levels. And we don't need this anymore because our last column, we will just return the customer average from S2, which is our subquery. And I believe, don't need a group by. I believe this should work. So we'll get the amount, customer ID, number 1. Here's all the payments they made versus the average payment. And then you notice for customer 2, they have a different average payment. Customer 3, and so forth. Okay. So how long did that take? Not too long, but imagine if you have a huge database, that could be orders of magnitude larger. It says 1.15 seconds, so 15 hundredths of a second or 14 hundredths of a second. So pretty fast, really. But it's a small table. You may come across tables with tens of thousands of rows, and maybe it's not so fast then. So let's see this result if we do a Windows function into Sequila payment. And then we don't need to do a group by here because we're doing a Windows function and we're telling it to partition by customer ID. Unknown column sale ID because this is now a payment ID. S dot amount. Okay. And then we want to average S dot amount over each customer ID. Let's just do this too. Like putting the customer ID in there. And it's not S1 alias, it's just S. Okay. So you see you still got the same value. So for the customers, that first one I remember is 3.078. You still get the average over the customers. You can just write it this way instead of writing it the subquery version. And in this instance, the Windows function didn't actually help with performance. That was 17 hundredths of a second. But over a big data set, sometimes things like this can make a big difference. Plus, you've greatly simplified your query also. And remember, these aren't the only 2 options you have. You also have the CTE option. You could calculate this first as a CTE and then use it in your query, and then perhaps that's even faster. I won't do that here. I'll give you just in for the sake of moving ahead, but I'll paste this for everybody to see. In general, the subqueries will be slower because I said what the database does, it has to get all of these records first before it can do the join to this table. Whereas this, it already has all of the records from the payments table, and you're just summarizing over this part. You're summarizing over these partitions. So it depends on the situation. You'll see it depends on the data set and situation. Always, if one way's faster or easier or whatever it may be. But you have another tool in your tool belt now to potentially do things in a more efficient way. And let me bring this back over. Okay. So you have all the different functions. You can use all these different functions as Windows functions, your regular aggregate functions. We just use an average. What we saw in the last lecture, we actually used a Windows function on a row number to be able to detect duplicates. So we did that in the last lecture without knowing what a Windows function was first. But it is a way that you could potentially do duplicates by some key. But just knowing the row number or the rank of a customer could potentially be useful. You can use these ranking functions as Windows functions. And then you could use value functions. So you can do the lagging 10 values. So that would include the current value and the previous 10, whatever you have them in order in the database. Leading calculation. So your calculation plus a few observations. Usually they're ordered by date. So it'd be like your current date plus the next 10 dates, or your current date and the previous 10 dates. Those are your lag functions, where you can get the first value, last value, or nth value over a partition. Great. Let's go over a couple of these examples. These should work pretty well out of the slides. So I'll go ahead and copy and paste these. Copy and paste. Oop, copy and paste these into Slack. Okay. So I copied the Windows functions. There are 3 examples. Just put it in this one. So first one, simple one. So this is like 3 examples. So you'll do an overall average, a group average where you're doing a partition, and then you'll do a rank. So the business questions are down below. The first one's pretty easy. So employee name, salary, and you don't have any partitions here. So you just have the average salary over everything as the company average. Now you could group, you could just do this group by and then have the same thing, but they just want to show, they're just showing you this example. So you do that. And you don't have, I don't think you have employee salaries in here either. This would be a different schema. Let's see if we have staff. I don't think I have a salary in here. Let's just do This isn't for the SQL schema either. I don't really have a good example here. I'll just describe these for now so we can do an example that comes from the SQL schema. So this would be over your entire, over all of your salary, over all of your employees. You get each individual salary and the average salary over all of them. So the second one is group averages by partition. So it's showing everybody's salary versus the company. Show everybody's salary versus their department average. So you have employee name, salary, and department. You can do the average salary over the department. So you imagine you have different departments as your data, or in your data set. You can do the average of everyone within department 1, everybody within department 2, everybody within department 3, etc. And then you do that and you get the average for that employee versus the department that they're in. And then with ranking, you can partition by department, but potentially you want to just rank everybody's salary by the department. So you have employee name, salary, and department. You do the rank function, and then you have the over, and then you have the partition by department. So it's going to take the top salary. It's going to put that as 1, second salary is 2, and so forth. If there's a tie, it will have the same number on both. You have to order it by salary to be able to do that, descending salary, so that it goes from top to bottom and it creates the rank from 1 to how many ever are in the department accordingly. So that's how it works. Unfortunately, I didn't check to see that those were in the SQL database, so we don't have concrete examples of those. But for the next slide, we do. Show everyone the next slide. So we have this exam. We do have it for this example. And this is one, it has a few joins, and it'll show you how you can do a concatenate over film. So we could break this into a couple of parts. So you can join multiple tables together and even do this group concatenate title. Then you can order by the title with a separator. So what group concatenate does is it does it over, it group concatenates the customer ID and first name, and it group concatenates all of the titles under that ID and first name and does it by separator. So it's a little bit a different function than the Windows function, but it is a type of Windows function. From customer, and then you have the customer, you have the rental, inventory, and film all together. So let's see how this works. Get all film titles rented by each customer. We'll put this in Slack also. So yeah, instead of listing, so the usefulness of this, instead of listing every title by row, you can concatenate them all into a single column. This is pretty useful to create that list. That's all in one field. So first, let's just see what this data looks like. And we don't need the group by. We can just join these tables together. And let's order by customer ID, just so we can see it a little bit better. Okay. Okay. So we have this customer. Her name's Mary. She has rented all of these titles. You see they're all in this long list. But what we can do is concatenate over this group. In order, now we're ordering by f.title, and we're concatenating over the customer ID and first name group. So customer, rental, film, inventory, all joined together. We can order the customer ID at the end, but we don't need to. And we're grouping by customer ID and first name. And we're just limited to the first three. So now Mary is that first customer, has all of these concatenated together. So this would be really hard to do in a query if you wanted a concatenated list like this. You'd almost have to, what would you do here? It would be hard because you wouldn't know exactly how many films they've rented. You'd almost have to transpose this field. And off the top of my head, I'm not sure how I would do that in SQL. Like you'd have to take all these rows or call that column and transpose it into rows like this. I'd have to think about, I'd probably ask Claude or ChatGPT how it could do it, but there's a function for it instead. Maybe I'd just recommend the function for me. Actually kind of interested. Just going to do it really fast. And it's usually, even if you're pretty vague, usually pretty good about figuring out what you're saying. How in SQL, MySQL, how can I take a long column of values, column of values for a customer, and transpose those, all of those values into a single field. Yeah, it came up with group concatenate right away. Group concatenate. It says don't try to loop through it. It says use group concatenate. Yeah, you'd have to loop through all the values and then concatenate them one by one. You'd have to use procedural SQL to do it without that function, which I'm not interested in doing if it already exists. But always ask what's possible. If you're trying to do something, ask what's possible, and it'll help you out with the result. Okay, let's keep moving. Okay, we are on the home stretch here. It always brings that same one there. Okay. Hold on one second. From the current slide, it's doing something weird. I'll just go with this then. Okay. So this is a slide usually introduced early in the class, but it's really important to think about from a performance perspective. So the way when you're thinking about the performance of a query, a SQL query, you always have to think about how their relational database is processing the data. So it always processes your tables, and then your where statement, and then your group bys, and then your havings to filter it out, and then your select statement and results. So why this is important in performance from a performance perspective is just in general, like the less amount of tables that you have to join from, or the less amount of subqueries that you're using in your from statement, that probably has the biggest, it'll probably have the biggest impact on your tables or on your query performance. So the tables that you're selecting for is going to have a huge, performance impact. So your where statement, one of the biggest things that you can do for your where statement is limit the number of records from each table as much as possible, so it has less process. So the query processor has less processing to do, or the database management system. If you were using a group by, say the less columns you group by, the better. It's not always possible, but the less columns that you do it over, the more performance that you'll have. And then selecting columns, so doing as narrow a data set as possible. That often, if you've done all of this, narrowing down the number of columns in the data set will often give you a multiplier effect as far as performance is concerned. And then order by is usually overhead, so you don't have to order by. You don't have to order by your results. You don't have to order in your result set necessarily. It's usually just additional processing. It's not required, and it's usually just additional processing that your data set has. But noting that this will also be better on smaller data sets to get your final result. So trying to narrow, if you're going to order, trying to narrow it down as far as possible before you're ordering. Doing your ordering is important. Okay. So with that said, there are some ways to design, they call it bad queries. I just call it inefficient queries if it gives you the right result. Bad, that's me as a data analyst thinking about it. But why is this a bad query design? You're selecting multiple columns, and not only that, you have multiple subqueries in your columns. So all of these have to process first before anything else happens. And then even in your where statement, you have this huge number of customer IDs that you're comparing your customer table to. So thinking about the tables that you can select from, your where statement, your group bys. We don't have any group bys in this. But then what can you do with your columns? And then this order by may or may not be necessary here at the end. But that's how I think about it. So why do we think this is a bad example? So multiple correlated subqueries forces table scans for each customer. So I'll do this a whole bunch of times. I'll do this and then try to join it by customer. You're repeating table access to the same table. So this customer table, you're using it 1, 2, probably 3, 4, 5 different times when maybe you don't need to use it. Reference it 5 different times. And index utilization. So we don't cover indexes in this class, but oftentimes tables will be designed for analytical purposes. So using indexes can be important. And there's some use of distinct here also. So distinct didn't really need to be used here. It's just calculate, it's overhead. So there's a lot that we can do to this query. Let's just go ahead and run it. Give this to everybody. Here's bad query design. This one I've run it in the past, so I know we can get an improved performance gain from this. Oop, once in a while when you copy and paste out of this, it doesn't paste that quote or apostrophe, right? Okay, let's run this and see what happens. So what is this thing doing? So first name, last name, we're getting the count for each customer as the total rentals for each customer. We're getting the overall sum where rental ID is rental ID. So for each, okay, so the sum of payments over all of the rental IDs for that customer. And then we are for the titles, we're getting each title for that customer. Order by rental date. Okay. So we're getting a couple different aggregate levels. This is like another way to do it. If you wanted a couple different aggregate levels, you doing it in your select statement and then joining it on customer ID. And you see it's pretty inefficient. Since it's not a ton of data, if you don't have a ton of data, your queries never really take that long. So that's like 27 hundredths of a second. So it does for each customer. Oh yeah, that's the last rental. So it's selecting the last rental that they had and just doing it all in the select and joining by customer ID. Total rentals, total spent, last rental. So imagine this could be a report potentially that you're creating. So what's a better way of doing this? So maybe you just want to get the results out to management and you're like, well, I can just write this way and it's quick and it works for the first time. So what is a lot better here? We have an efficient joins. We have like a minimum number of tables. We have rental counts. We have it just for active customers and their rental dates defined. In the order grouped by customer ID, first name, last name, rental count. And it's not exactly the same query because we don't have the last. We don't have like the last movie rented. But why is this efficient? So it's always start with the where clause or the tables. We're only using the customer table once, and we're just using the rental table. So we're just using two tables instead of the customer table like 5 times and rental table along with it. In the where statement, we're taking that initial table and we're limiting it down as far as possible. That would help with any tables that you're joining, is to limit them down as far as possible as far as the number of rows is concerned. All right, so we're grouping by just the columns that we need. We can order by rental count at the end, it's fine. And in the query, we are just getting the columns that we need. So it's pretty narrow and thin with no extra overhead with columns that we don't need. So specifically, some of these is efficient join syntax. It uses inner join. Clear, it's readable. That makes it good, just a good query overall. You only retrieve the necessary columns, which makes for faster data transfer and retrieval with the database, relational database systems. And then you're filtering early, like I mentioned, to just the row, also just the rows that you need. So the more you can reduce the rows and columns that you initially need, the least amount of joins that you need, the more efficient that it becomes. So joining principles, start with the smallest result set. Try to start with a table that you can have the smallest, you can make into the smallest number of rows. And then even if the bigger tables are joining to it, it goes really fast. Join condition placement, always put these in the on statement. You can put them in the where statement, but we don't learn that in this class, but it's much more efficient when you put it in the on like we learned in this class. And then if you had indexes on the table. Okay. So let's go ahead and see this good query. Go ahead and copy and paste this. And I'll put that in Slack. So let's see how fast this query runs. 584 in 0.15 seconds. So it's a good increase over the other one. It's not exactly the same query. So let's do, I want to do this. Just add this other column in here. This last rental column and see how it does. So it's you'll get the last rental for this, the last rental for this customer. Let's put this in a little better format. Okay. And then we'll also want to group by this last rental. Okay. So I believe we can group by the label in MySQL, whatever you label this calculation. That's actually a lot worse. So that took 1.4 seconds. Hide the way the query is initially designed. And then adding this to it added actually more overhead than how it's designed. So it's all about query design. You have to try a few different things, a few different combinations to the right arrangement of it being the best query or most efficient query for your purposes. And now we've learned some new tools. You could even do a CTE here. Calculate that first. Yeah, why don't we do that? We'll go ahead and do a CTE and see how that calculate last rental that way instead. Let's go ahead and go back to my CTE example so I can just copy and paste the syntax. And I did drop it earlier into here. So let's just remove that. And let's do a CTE. Okay. I bet this is going to be way better. It's going to be way better. Okay. Efficient joins. So let's take that last film. Let's just calculate that in a CTE. That last rental. Call this CTE last rental. Or created in a temp table either way. CTE might even be faster. Okay. So we're also going to need a customer ID because we're going to need to join the CTE to our main query. So let's see what this does here. Maybe I don't need the customer. Do I need the customer ID? Order by, rental date, limit 1. No, shouldn't. Okay. Let's see, what issue would I be having here? From film.f. Customer and title. Unknown column C dot customer ID. Okay, so this is an example. We usually almost always use on clause, but you could do inner joins in the where clause, but it's much less efficient, but we're still going to run it anyway. Okay, there's customer 373's. This isn't quite right the way it works. I'd have to redesign the query for the CTE. You'd have to get all the customers in their most recent title and then join it to this table because you're joining this by customer ID. Well, you can read it. The point is that you could redesign it the way you need to with a CTE or a temp table, and this performance would be much better. I thought it might be a little bit easier to redesign the query than that. I have to think about how I want to calculate that and then join it by customer ID. You have to get the most recent film by customer ID and then take that and join it to your main query. So you can always redesign these queries for better performance. What I found super useful in my career is talk to a data engineer or a database administrator or someone who's really senior who has just redesigned these queries a lot, and they'll just see it for you. Either that or use ChatGPT. Use ChatGPT or Claude to ask it to redesign this for you. It's like doing all these examples. Can be pretty vague about it, probably. Just tell it to redesign this query. Sometimes it needs to know your database schema to do it right. There we go. So it's doing the row number. It's getting the first title for each customer. And then it actually does more than one CTE. It does a nested CTE. This is a good example. Let's see if it actually works. Then I'll give this to everybody. Okay, so here's what it did. Okay, so it gets the most recent title for each customer, or maybe it doesn't. Oh, it has the rank here, so it's giving me the rank. And it's just going to do all of those for now. It takes this correlated query, or not correlated, this CTE, uses it in a second CTE just to get rental counts by customer ID. So to see this in action, you'd have to do something like this. And then you'd have to run both of them. Okay. So it has the rental counts. This is just the rental counts itself. This actually is a nested CTE because, oops. What did I do with it? Let's just repaste all of this. Okay. So it uses this rank last. It uses the rental counts. It takes the last rank. It left joins that where rank equals 1. So it gets everything up here, but it filters it down to the most recent. Filters it down to the most recent title rented. And then it also takes this rental count CTE and it joins that to customer. So it takes both those CTEs, those nested CTEs you used, to break it into multiple parts. And then I ran it with okay efficiency. I think it was faster than the initial query. But it gives you the same result, and it's redesigned. People who have experience with this in the database, the people who are the experts of the database, whether it's a database administrator, a data engineer, I guarantee if you ask for their help, they could design this query to help it be as efficient as possible after you create it. Oftentimes data analysts are just interested in getting the right answer, which I know oftentimes I am. But it's not the most efficient way. It's the way you think about putting it together, bringing it together initially, and then there's some work that you can do to improve the query performance and make it much better and still get the same result. All right, so what have we done in this class? We've done a lot. So Windows functions, we use those for advanced SQL, some complex queries, learned about Windows functions to eliminate self-joins potentially. Make it more efficient for the analysis in those different aggregate levels of rollups. Use those wisely, it says. Well, rollup and cube, those are two different types of rollups, but proper aggregation, doing it right, it reduces the data movement and then how much you have to bring together. And then we learn performance optimization here in hour 2. So in hour 1, we also covered a lot there with temporary tables and CTEs, standard and procedural SQL, and how you could use functions and stored procedures, and some techniques and how to create them. And then also some practical examples, but how to look for help using generative AI or examples out on the internet. We burned through it. I didn't think that we would get through this today. There's a lot. Any questions? Would anybody like some more examples? We covered some, but does everybody need a break? We have about 10 minutes left. So I'll leave it open to everyone if we covered enough examples or if we'd like more. Any questions you'd like to ask? I have a few more examples if people would like to see it.
Sure, that'd be great. Thanks.
A few more examples, okay. Thought I'd just leave it open for any questions because we burned through it today. Let's just cover some more examples. Let's do a hand. Let's see what we have here and do a pretty hands-on example. If I can find my cursor. Yeah, we'll save. And I'll recompile all these SQL files. I need to do that from the last class. Just go back through all these lecture slides and make sure the SQL queries correspond to what's in the lecture notes. It's something that I can do for everybody so that you have that and you can look back on the queries in the notes and run these, whether it's on this database or other data or your own database that you set up with the world database and the SQL database. All right, let's go ahead, pull up some additional lecture examples here. I have some extra ones here. I'll try to find the most practical example. I plan on making the homework, so it will cover the data cleaning, and then it will cover what we learned tonight. I'll try to make them very practical data analyst type examples, so you can practice, take your skills and really practice things that you would use on the job as a data analyst. Let's see. So there's a lot that we could cover here. Let's see, start from the top and see how far we can get. Matching, pattern matching. Just got to find my notes. Be 1 second. Let's see what I did with that. Oops, hold on. I suddenly lost it. Just a moment. Had them on my desktop. Okay, almost there. Okay, hands-on lab work. Let's do the first one. We have a CTE, then we have a Windows function, and query optimization. I could send this to everybody too. Guided exercise. CTE for multiple step analysis. Okay. So here's a business question. We'll just keep going through these. We'll do one CTE. Business question. Find customers who spend more than the store's average and show how much more they spent. So perfect for a CTE, multiple steps. They calculate their averages and then how on each transaction, how much they spent and what their and then also what their current spend is versus their average, which transactions, identifying particularly which transactions did they spend more on. Okay. So the first part we can do store ID with the CTE. We can see by store. Let's see. Okay. So yeah, there'd be even multiple stores. So really understand it. First, like I always say, it's important to understand the business question at hand. So you have this one customer who spent more than their store's average and show how much they've spent. So a customer can actually belong to more than one store. So it's important to recognize that. Create a CTE to calculate the average spend per store. Okay, so we did that. And we're just looking at this part of it. So we're just going part by part. Okay, that's the result that we get. After each step, I'd do something like this. I would just take a look at the result of the CTE. Make sure it's exactly the result that you want. So step 2, you can use that CTE to find customers who spent more than their store average. Okay. So we're going to write in their CTE here. I think this will be a good example of using the result of one CTE with another. All right, so you have store averages. Okay. So this is a continuation of the first part. just leave this. Okay. Step 1 was that. We just built that. So step 2 is now building upon store averages. So we have that first CTE. Then you have customer totals. So this customer totals is our second CTE, has customer ID, first, last, store ID, total spent. Customer ID. So let's go ahead. So we now have, if we do both CTEs, you have the customer IDs, the total spent, the spending average at each store, and anything that's above average from your customer totals, your store average, and then you're seeing where the total spent is by store is greater than your average spend by store. So this looks like pretty complete query. So this is all the examples. So it'll be customer, their total spent at a store, total spent, the store average, and above average. So let's see, let's dive deeper into seeing how this works. Let's just do customer 526. Okay. I kind of want to understand this a little bit better myself. And I would put the where after the join. Customer ID clause is ambiguous because we need to correlate it with the table so it knows. Okay, so the store ID to the average spending is $4.92. Okay. So let's do customer ID equals 526. I think I already know what's going on with this query. So we're going to do customer totals. Let's see. You have an error in your SQL syntax from customer C because I need to put that below the join. So this is how I'm doing it. I just track it down by one customer ID to see exactly what this is doing. I think this is actually summing the store. So store ID of 2, your total spend is $221.55. I kind of like a customer that has more than one store. This customer only has one store. So like really tracking down, working with these and tracking down your data issue. Store 1. Oh, this is the average by for all customers in that store. Okay. So this is like an all customer average. It's not like their store average, then the store average. So this is like over all customers. The store ID, what's the average spend over all customers? This would be the average spend per customer. This would be the total spend for each customer at that store. So if I do this, this would be all customers at all stores. Okay, this would be all customers at all stores they spent at. And then we're selecting customers whose total spend is more than the average spend at that store. So you're like, really, this query is like identifying standout customers or customers who spend more at that store than the average customer. Okay, so we have to run both parts, of course. We have to run the CTE from the beginning. And then that would be customer 526 spent this much. And it'd be helpful to see the store ID in the final result. Customer totals. So if I took customer totals, I want to see the store ID too, because I want to know like what store we're talking about with the customer. Okay. Let's see if that should make a difference. Now we see what customer, what store, what the store average is, and how much they spend at that store. All right, so customer 526, it's store 2. His name's Carl Seal. He spent $226.95 at the store. The store average is just $4.20 for each customer. So he's $217 above average. And that's the idea as a data analyst. You're always thinking about, like, is this a result or am I putting this together right to answer the business question? Or does this result seem right? Or can I break it down into parts? It's really like problem solving and then asking yourself, like, does this result make sense? Like, does it answer the business question? Or even like, sometimes the business question's kind of vague. Like, would this be something that somebody would be interested in looking in who ever asked you that question? Because without that store ID, you'd be like, well, I don't know what store ID that is, what the store average is. It's some store. Oh yeah, now it's store 2. Like, what information do you need to make an informed decision? And then how do you bring that all together here in small parts? Well, I'm over time now. I do have a couple more exercises that I could send everyone, but hopefully this is the first time I've taught this. So hopefully it's like useful. It's a really, like, these last 2 were hands-on, but this one in particular is new. So hopefully you found it helpful in what SQL looks like for a data analyst, from a data analyst perspective, and using these different pieces to help you put together data. And how you can do it efficiently and answer those questions. We're kind of an experiment in this, but these things, but putting everything that you learned together in SQL, it goes by fast. It's a lot to cram in. And 7 classes makes it even tighter. 6 classes technically. I'll have a homework out like this tomorrow morning. I'll work on it, or at least as soon as I can. It'll be similar to this, answering business questions like this and using CTEs and temp tables and efficient design and Windows functions and things like that.
Thank you so much. Have a good night.
You're welcome. Take care, everyone. Have a good night. I'll get back to you with a couple things soon. And take the final. Good luck on the final, and see you Wednesday. Oh, Simone, I didn't answer your question. Are you still there? Oh. All right. All right, let's finish this up. This is actually the wrong title for the class that I put on here. So this class was Advanced Database Functions and Performance. We learned all about some of the advanced database functions you could use and how you'd use them as a data analyst, and stored procedures, functions, and stored procedures and functions and temp tables and CTEs all can be useful as a data analyst. Then we learned about different ways to calculate aggregates, past just doing it in a brute force manner or doing it through subqueries, and then more about SQL performance, and how to design queries to be as effective as possible. So I'm Jeremy Bergman, the instructor for this class. The final class will be the final exam. Give students a chance to do that and share some alternative content that I have taught in this class in the past. So it's been exciting, and this is pretty much the end of SQL content. So I'm Jeremy Bergman. The next class, be a little bit more about some data engineering things, and it'll be wrap it up. So for everyone, thank you, and see you on Wednesday for the final class. Good night.